Okay, next we've got Markos Georghiades from a16z talking about Jolt, the zkVM that they've been building in-house. Welcome to the stage, Marco. Jolt, a simpler path to high-performance zkVMs.
All right. Good afternoon. I'm Marco. I'm an engineering partner here at a16z, and it is really my pleasure to be here to tell you all about Jolt. All right, here's some, the key. The keys aren't working. Oh, I got it. OK. Quick disclosures, and all right. I have to show you them. Sorry. This talk is really about myths and misconceptions. So there's been a lot of great progress this year. But with this great progress, unfortunately, a number of myths have appeared about the conventional way to design a proof system. And so this talk is really about addressing some of these myths and pet peeves that we have here at Jolt. Before we get into the myths, we will first begin with some context that is very necessary. Now, as I alluded to, the progress has been quite good this year. And with this progress, seemingly, every proof system other than Jolt has converged to a very similar construction. And Jolt, as we will see, is very different. But I pose this as the final debate, Jolt versus hash-based provers. So here are the metrics today, and the metrics that people care about. So if you take a P99 block today on ETH proofs, a Stark prover is performing at about 14 seconds with 1650/90s. The proof size today varies a lot for a Stark prover, anywhere from 220 kilobytes to over 1 megabyte. The memory usage today is bounded but large, and when I say large, I mean 8 to 10 gigabytes. Jolt today is about 70 kilobytes proofs, and we are using 330 bytes per cycle proven. In 2026, we want to be at sub 1 second proofs. Here are the main design choices of zkVMs. So today, most zkVMs are designed for succinct blockchains, as is Jolt. Jolt will be very effective for that. Jolt is also the only RISC-V zkVM that I know of that is suitable for client-side. Jolt will not use recursion and will not use circuits. And these two design choices are reflected in the fact that Jolt's core prover is implemented in only 40,000 lines of code. Throughout this talk, I will be mentioning a few particular upgrades. So in particular, GPU Jolt, streaming Jolt, and Lattice Jolt. So just keep an eye out for those as I go through the content. All right, so let's get to the first myth. The first myth is that we can just throw GPUs at the problem, and we're going to get a faster proof system. All right, so to explore this myth, I begin with a fact. Fact, if I give existing zkVMs today 2,000 GPUs, they are not going to prove ETH in 1 second. So why is that the case? Well, the implication is very clear. We have suboptimal parallelization. Jolt, on the other hand, has this property, I will just call it partition-friendly data. It's actually very simple. All it means is that in this case, I have an example of polynomial binding. It's a very common operation in Jolt. You can take the data, the coefficients, you can split it into chunks, like 4 chunks. You put them each onto a GPU, and each GPU is very happy, and it does its own work. And there's very little latency and cross-communication overhead. So Jolt is very friendly when you take the data structures of proving, and you split it across multiple cards. Now, Jolt, other than being partition-friendly, is also the fastest zkVM today on a CPU. Jolt today is nearing 2 megahertz with a 32-core Threadripper. You will also notice that Jolt is very workload independent. What that means is that Jolt cares very little about the underlying workload. What matters to Jolt's speed is simply the number of cycles being proven. I will also note that today, 31-bit Stark provers are performing at around 3 to 6 megahertz with a single GPU, and Jolt is dangerously close to that territory. Right, so then I say, Jolt will prove 1 second with 16 GPUs. The math is very simple. Take a P99 ETH block, which is about 1 billion cycles. Jolt proves at about 2 megahertz today. And Jolt has this partition-friendly property. And so we expect an 800-fold increase. And, well, the math says ETH blocks will be proven in under 1 second. With streaming, I expect single GPU Jolt to also be as fast as today 16 GPU Stark provers. All right, let's move on to the second myth. That was all about these very large statements, yeah? And what about the small things, so the client side? Well, largely, that has been neglected by zkVMs. I have this fun app This app is really the simplest possible wrapper that I could make around Jolt. It is literally a simple function call into Jolt's CPU prover. I'm not a mobile dev, so I apologize for the bad UI, but I'm going to just click this button, and we're just going to see what happens. What this button just did is it's proving Jolt on my phone. It's proving 30 cache acts just for fun. And yeah, so we'll just wait for it to finish. OK, it's done. So the proof finished in 4.7 seconds. It used, the screenshot's pretty accurate, actually. This one used exactly 246.6 megabytes of memory. And as far as I know, it's the only zkVM that's RISC-V based that is anywhere close to these metrics on a phone. So I expect Jolt will be the best zkVM for client-side proving, and for big statements, too. Yeah, so why do you want this on a phone? Well, OK, current existing solutions for client-side are not adequate. They, first of all, involve circuits, and I want to kill circuits. Be very clear. I will talk about this shortly. They have proof sizes that are just far too large, and sometimes they do not have succinct verification. And sometimes I've heard some ridiculous things, like having to download verifier keys that are literally take longer than the actual verification itself, which Jolt does not have this problem. And I think that's pretty ridiculous. We had that in 2025. OK, so I mentioned circuits briefly. Let's talk about why I don't like them. OK. Jolt does not use circuits, as I mentioned. In replace of circuits, we have batch evaluation arguments. To be very clear, circuits are just the largest source of bugs. They are. And here on the right, I have a code snippet which shows the auditable surface of a single instruction in Jolt. So it's like 10 lines of code. You implement the multilinear extension of the AND instruction in this case, and that's it. The bottom line is that this is better for your auditor, and it's also better for the machine that's going to extract this and do formal verification. So I think we would rather have instructions that look like this than circuits, and I hope you agree. OK, so the second largest source of bugs, arguably, is that of recursion. So let's talk about recursion. What do people do today to control memory in a zkVM? Well, what you do is you have this big execution trace. You chunk it up into a bunch of pieces, and then you're going to prove each piece independently. Once you prove each piece independently, you have to aggregate them, and then you get this final proof. You also have the burden of having to prove the memory consistency between each of these chunks. Now, why does this suck? There's three main things. Number one, it is very bug-prone, and at a protocol level, it is complex. Some zkVMs today spend 2/3 of their time doing this recursion, so it is very slow. And some zkVMs, to make this faster, have to use curves, which defeats the purpose of being hash-based. There is also the minimum high memory requirement of 8 to 10 gigabytes, which makes these zkVMs infeasible for a phone. OK, so in replace of recursion, we use streaming at Jolt. Streaming is, when I say streaming, I mean a streaming algorithm. It does not have additional circuits, does not have an additional pipeline, and we are just streaming the trace and the execution trace through the prover. What's nice about this is you can easily tune your proof pipeline depending on the desired RAM and number of threads available. Just to kind of explain how this works, so you have, instead of having to prove each chunk independently, you take one contiguous chunk, you feed it through the proof system, and then you take the next chunk, feed it through, and you continue until you pass through the trace. In the streaming paradigm, you have to go multiple times over the trace, since we are lazily evaluating it, and particular O log n times. But what is nice about this is after the first pass, you can parallelize this process. And so in practice, for GPUs especially, this is quite cheap. OK, to all the people out there who don't like curves and say that today Jolt indeed uses curves, we have a good answer for this. Enter Lattice Jolt. Lattice Jolt is basically just curved Jolt. It has the same asymptotics and concrete values as Dory Jolt does today, but with modular SIS assumption. So Lattice Jolt, we expect to be 4 times faster than curved Jolt today because of the fact that we get to use a 128-bit field. We will talk more about why we use such a big field, but the point is here is that we expect Lattice Jolt to have the same concrete values, the nice small 100 kilobyte proof sizes, and we expect that the performance of CPU Jolt will actually match or exceed current 1 GPU provers. Now, in the end, I actually expect, because of Jolt's uniquely modular design, that we will be able to support all primitives, and the developer will just be able to pick whichever assumption that matches their post-quantum risk appetite. We are still working on hashes, but today, lattices and curves are great options for Jolt. Right, OK. How are we doing at time? Yeah. We have one more point that we will make today. So the prevailing approach that a lot of that Stark provers use is that of 31-bit fields. So what I mean is that, say you have like a mul rs1, rs2, this instruction. What do Stark provers do today? Well, because 16 times 16 bit multiplication overflows a 31-bit field, what you have to do is this byte decomposition. So this like blue line here, or this blue layer, is byte by byte decomposing each of the 64-bit registers. And then now you're going to perform byte by byte multiplication. And then you're going to concat the result back into the field. So what does Jolt do instead of this? Jolt uses a big field. Jolt can directly embed the register values or the RAM values into the field and then do a single field multiplication. Now, it turns out that comparing the two approaches, so having faster multiplication or having a single field multiplication, that you come out on top by having one slower multiplication rather than doing the byte decomposition. The byte decomposition creates a lot more work, and this approach is one of the main reasons why Jolt is many times faster on a CPU today than other provers. All right. So let's do a quick recap here. I threw a lot of information out. So there were 6 things that we targeted today in this talk. And yeah, I'll just give you the rundown. Jolt today does not have a GPU prover, but we expect Jolt to run at 1 second or under with 16 GPUs. Jolt today is the most performant RISC-V zkVM on a phone, and I expect it to be the choice going forward in 2026 for client-side proving. Batch evaluations are both simpler and faster than circuits. Circuits are bug-prone, and they should die. And streaming is simpler and faster than recursion, which is also a very brittle primitive. Jolt today works well with curves and will soon work well with lattices. And lastly, we avoid this nasty byte-by-byte decomposition that makes other zkVMs slow. All right, that's about wraps up my time. Last thing here, here's a nice photo if you want of the 2 different constructions. These are the main ingredients of Jolt for Starks, and yeah, that's it. Thank you very much.
All right, amazing, Marco. Got time for a few questions, so let's see here. Why are you currently not first on ETH proofs? How many assumptions do you have in the sub 1 second block proof time?
Right. So we don't have a GPU prover. When the GPU prover is available, or when we are faster than GPUs on a CPU, then we will hook up to ETH proofs. That's the first part. To answer your second question, remind me.
How many assumptions are you using, I guess?
Yeah, I mean, there was just 2 things in this equation. I will actually preface this by saying that people traditionally ignore how fast a prover is on a CPU because, well, we want GPUs for large statements. But avoiding this metric, which I made it very explicit today, makes it very hard to reason about how fast these provers are actually proving VM execution. So the 2 things, the assumptions made here is that, number 1, Jolt is the fastest prover on a CPU, and Jolt is doing the least amount of work per cycle out of any proof system, period. And second of all, Jolt is very friendly when you throw more hardware at it. So I expect, because it is the fastest thing, like the base amount of work, and because it is very parallelizable and friendly when you partition it in a distributed system, I expect Jolt will be the fastest prover on GPU.
Great. You have our RISC-V 64 iMac right now.
Yes.
Which ISO will you target in the long run?
RISC-V.
Okay.
We believe that RISC-V is a snark-friendly instruction set. Yeah.
Is Jolt planning to do sub-blocks as well?
Don't think it's necessary.
Nope. OK. Why is being the fastest RISC-V-based zk prover on a phone important? If I'm on a phone to prove, why would I not prefer WASM?
Well, Jolt will work for WASM and for native execution.
OK.
Yeah. And I think it will be as far as RISC-V zkVMs go, will be the best for that. I think you can always do better with bespoke provers. But in the long run, I don't see this as a maintainable solution.
Let's see here. Can you give more details on the parallelization of the execution?
Which part, the streaming or one in particular?
I wish I had the follow-up.
Was this the beginning, or was this in this slide?
That's all I have. Okay. Maybe we could go to another question.
Yeah.
Is streaming Jolt also super parallel friendly? You need an initial serial pass similar to other zkVMs, right?
Yeah. So you have to generate the trace once serially. which is known to be fast on GPUs. And then afterwards, you can basically put these checkpoints, and these checkpoints, you can save the memory layout, and then you can now do things in parallel. So yes, it is quite friendly. This streaming, this lazy evaluation of the trace has very little to do with the fact that the rest of the prover and the sum checks are already very parallelizable.
Great.
Yeah.
Thanks again. Round of applause for Marco.
Thank you.
Thank you.